Ever wondered how AI creates new images, videos, or music? That's the power of generative AI. Today we will explore it by building your first GAN, Generative Adversarial Network. Hi everyone and welcome back to the Skill Lift channel. I am Shahid, your AI ML guide with over a decade of experience in the industry and academia. Before we dive into the generative AI, take a moment to like, subscribe, and share this video with your friends. It's time to unlock the secrets of AI together. Today we will use Python and PyTorch library to create a GAN. By the end of this session, you will see how AI generates new handwritten digits from scratch. So let's begin. Hey everyone, welcome to today's tutorial. Okay, in this tutorial video, we will be diving deep into a powerful AI model that is Generative Adversarial Networks or GANs for short. And we will walk through every line of code in a simple step-by-step manner so you can understand the magic happening behind the scenes. Whether you are a beginner or someone with a bit of experience in deep learning, this video is for you. Okay, so we will be using PyTorch for this tutorial, and the goal is to build a GAN that learns how to generate images of handwritten digits, specifically from the MNIST dataset. So this model is a combination of two parts, the generator and the discriminator, and they work together to create realistic images. Think of the generator as an artist and the discriminator as an art critic. So the two of them constantly challenge each other, which results in progressively more realistic images. So let's break down the code and understand how it all fits together. I'll explain each part in detail from the setup to the final output. So let's get started. Okay. So before we dive into the code, let's understand what a GAN actually is. Okay. A GAN actually consists of two models. Okay, as explained earlier. The generator. Okay, the first one is the generator, which creates new data like images from random noise. So you can think of it like an artist drawing the random sketches. The second one is the discriminator, which evaluates the generated images from the generator, trying to distinguish between fake images that is produced by the generator and real images available in the form of training data. So it's like an art critic judging whether the artwork is fake or real. So both of them are trained together. The generator wants to fool the discriminator while the discriminator tries to be a better critic. As they train together, the generator gets better at creating realistic images, and the discriminator gets better at detecting fakes. So this adversarial process is why it's called a generative adversarial network. Okay, all right, let's jump into the first part of the code, the configuration and the setup. Okay, so prior to this, we are no first thing is we are going to import the libraries and packages. Okay, so here we are going to import the library torch and all the necessary modules within the torch package. Okay, and matplotlib to plot and to plot the visuals. Okay, display the results. Okay, so in the configuration, okay, the first thing is the latent underscore dim equal to 100. So this is the size of the random noise input that will feed into the generator. Essentially, we are saying that we will give the generator 100 random numbers to start with, and from there it will generate an image. And next is image underscore shape equal to, within the brackets we have written 1 comma 28 comma 28. This specifies the shape of the images we are working with. In this case, we are using grayscale images of size 28 into 28 pixels or 28 by 28 pixels, just like the MNIST dataset. The next one is batch size equal to 64. Okay, here the number of images the model will process in one go during training. Okay, so we will use batches to speed up the training process. Next is LR equal to 0.0002. So this is the learning rate, a key hyperparameter that controls how much the model updates with each step. A smaller learning rate helps prevent the model from making drastic changes to the weights. Okay. Next is number of epochs. N underscore epochs equal to 10. So here this is how many times the entire data set will be passed through the network. More epoch means more training and ideally better results. Next is device. Okay, so device equal to CUDA. Okay, CUDA, CUDA. If torch.CUDA is available, okay, we'll use CUDA, else CPU. Okay, this is a fancy way of saying use the GPU if possible, otherwise use the CPU. Because GPUs are much faster than CPUs for training deep learning models. Okay, so the next, let's take a look at the generator. Okay, so this lines of codes is for the generator class. Now this model generates the fake images. Okay, here's how it's structured. Okay, the first thing is the generator is a simple feed forward neural network with several layers. Okay, let's break it down. Now the first thing is latent, dim equal to 100. We already know this is the size of the random noise input. Okay, here nn.linear with latent dim 128. Okay, this what it denotes, the first layer takes in the noise and passes it through a linear transformation to a 128 dimensional vector. Okay, next is neural network dot ReLU. Okay, what does it mean? After each linear layer, we apply this activation function. Okay, this is commonly used because it introduces non-linearity, which helps the model learn more complex patterns. Okay, the next layer increases the complexity of the features. The 128 dimensional vector goes through layers of again 256 and 512 units. Okay, now last one is this, what, tan h. Okay, the final activation function, which is tan h. This quashes out the output values to be between -1 and +1. So this is very important for image generation, as you know the pixel values in the MNIST dataset are normalized between -1 and +1. Okay, so finally here this line of code, okay, this reshapes the output into the final image shape. The model returns an image that's shaped like 1 comma 28 comma 28, okay, which is the shape of our MNIST images. So now let's move on to the discriminator. This is the part of the model that judges whether an image is real or fake. Okay, so the discriminator is also a neural network like the generator. It works similarly to the generator, but with one key difference. Its job is to output a single number between 0 and 1, which indicates whether the image is real or fake. The first layer takes the image, flattens it into a one-dimensional vector with image.view. Okay, img.view function. Okay, this is very important because neural networks typically work with 1D vectors. Then the image goes through a couple of fully connected layers with activation functions like ReLU. Okay, the final layer outputs a single value between 0 and 1 using the sigmoid activation. Okay, using the sigmoid activation. So what will happen, if the value is close to 1, the image is considered to be real. Now, if it is close to 0, the image is considered fake. Okay. So the next thing is the training loop. Okay. The training and the training loop. So this part, okay, this entire part. So, this is the core of the training process. Okay. Which is the training loop. Now, this loop is where the magic happens. Okay. Let's go step by step. First, we iterate the data set for n epochs. Okay, we will iterate the data set for n epochs. Each time we pass through the data set, the generator and discriminator get better. Okay, so this imgs is equal to imgs dot to. In the bracket we have written device. Okay, what does it say? We move the images to the device, okay, that is GPU or CPU, depending on what's available. Okay, we have some devices where we have only CPU. Okay, there is no GPU installed, so no GPU, the GPU is not available. So in that case, either it will go first to the GPU. If GPU is not available, then CPU. Okay, then the generator generates fake images. Okay, fake images from random noise. Okay, from random noise. So then we calculate the loss for both the generator as well as discriminator using BCE loss. Okay, BCE loss. So the generator tries to minimize its loss by fooling the discriminator, and the discriminator tries to maximize its loss by distinguishing the real from fake images. Okay, so finally we update the weights of both models using optimizers. Okay, and this is the core part of the training. Okay, the back propagation and weight updates. Okay, so every 5 epochs we save the generated images. Okay, every 5 epochs we save the generated images to see how the generator is improving. Okay, so here this happens. This gives us the nice visual representation of the model's progress. So we use the torch vision. Okay, we use the torch vision library to save the images, and we arrange them in a 5 by 5 grid. Okay, so we'll run this when we run this program. Okay, so this is how the output is produced. Okay, the epochs are performed. For every epoch, we can see the discriminator loss and the generator loss is calculated and it's being displayed. Okay, so it takes a bit of time, okay, to compile the entire program and give the output. So this is how the GAN is being programmed. Okay, or develop a GAN. Okay, so and that's it. You have now seen how we build and train a GAN from scratch using PyTorch. The generator creates fake images, the discriminator tries to detect them, and together they improve over time. So by the end of training of this epochs, the generator can create images that look very similar to MNST or MNIST digits. Okay, so this is what about generative adversarial networks using PyTorch. If you are amazed by generative AI, imagine mastering this and more in just 30 days with our AI ML Bootcamp starting January 6th. Learn generative AI, deep learning, and NLP. Build 4 real-world projects like chatbots and image classifiers. Get rupees 12,300 worth of bonuses, including templates and certifications. Limited offer. Register for just rupees 499. Seats are filling fast, so click the link in the description now. Don't forget to like, share, and subscribe for more exciting AI tutorials. Drop your questions in the comments, and I will see you in the next session.